When we say the word thermal energy, what we're really talking about is the energy that an object or a system possesses that is responsible basically for increasing or decreasing its temperature. Now, what causes that temperature increase or decrease, or that movement of thermal energy within the object? Well, it's really how much its particles are moving, and if given certain conditions, it'll move less, and if given other conditions, it'll move more. Because Earth itself is a large mass that occupies a certain space, it too can have energy within it, and that's based on whatever particles it consists of. And so what you'll notice is that the thermal energy transfer within the Earth varies from place to place. Some areas like the equator absorb that thermal energy very well and circulate it pretty well within its limits, and so it stays relatively hot. Other spots in the Earth, like the poles, don't absorb that energy very well and in fact reflect most of it back, hence it tends to stay relatively cold. Now, there are several factors that enable an object to circulate its thermal energy within its system. One of the main ones, which we'll be discussing in this video, is something called specific heat capacity. And the specific heat capacity really is the amount of energy that it takes to raise 1 gram of a substance by 1 degrees Celsius. Essentially what you're doing is you're assessing how long it takes for something to heat up if we give it a certain amount of energy. Now, not all objects are the same. We know that certain objects conduct heat a lot better than others, and the real reason that is because they have different heat capacities. The rule of thumb is the lower the heat capacity an object has, the higher its temperature change is going to be, or the hotter it's going to heat up and the faster it's going to heat up. While by the same token, the greater specific heat capacity an object has, the longer it's going to take to heat up and the less likely it will heat up, or the lower the temperature change will be when you apply a certain amount of energy to it. The main heat equation that governs a system's thermal energy behavior is this one: Q equals mc delta T. In this equation, the Q represents a thermal energy in joules within the object, and the M is the mass of the substance within the system that we're measuring in grams. The C represents the specific heat capacity of the object, and that's of course measured in joules per grams degrees Celsius. And then the delta T, or the triangle T over here, represents the temperature change in degrees Celsius, and that can also be expanded to T final minus T initial, or the final temperature of the object minus the initial temperature of the object. So our first example reads, how much heat is needed to raise the temperature of 462 grams of water from 24 degrees Celsius to 80 degrees Celsius. So if we're labeling our variables here, this is the mass, the M part of the formula. This is going to be our Ti, or T initial, and the 80 degrees will be our T final. The specific heat capacity of water is 4.19 joules per grams degrees Celsius. Now, this is a value that you can get in most thermodynamic books. In all exams, they're going to give you these values, so we didn't solve for this. Assume that it would be given to you within the question, or you'd have access to it when you're solving a problem like this. With everything that we need, we can now plug in the formula. Remember, we are solving for the heat that is needed, so that is the Q. So now plugging in everything as follows. You would then plug this in your calculator. I would recommend using brackets, because especially when we're working with decimals and those kinds of digits, it is best to put everything in brackets. And when you plug this in your calculator, you get a large value, which we're going to condense into scientific notation for the sake of significant digits. So we see that we have 3 significant digits here. So we're going to do 1.08 times 10 to the 5 joules. For our second example here, it asks how many grams of H2O can be heated from 20 degrees Celsius to 75 degrees Celsius using 12,500 joules of energy. Well, in this question, we're actually isolating or solving for the M. We have the Q, which is 12,500 joules, and then we have the initial and final temperatures over here. Again, isolating for mass, we're going to divide both sides by C delta T. And that leaves us with Q over C delta T is equal to M. And now that we've isolated for M, we can just plug in the values that were given to us. Plugging in these values carefully, we then get a mass, if we comply with the significant digits, of 120 grams. Another term that comes up when it comes to these heat calculations is the latent heat of vaporization. As heat circulates in a system, you're going to get changes, or phase changes, I should say. I was about to say changes of states, but it's more appropriate to say phase changes. And so the latent heat of vaporization is really the energy required to evaporate a liquid to a gas. And the formula that we use for it is L, which would stand for the latent heat of vaporization, is equal to the Q divided by, it could be the mass of the substance, or your heat divided by the amount of moles of the substance. It just depends on what the question is asking. Another thing worth mentioning about this formula is that your latent heat of vaporization is going to be often in kilojoules per gram, or in this case, if it's molar enthalpy or molar heat of vaporization, it's going to be kilojoules per mole. And so the first question here says, find the molar heat of vaporization. So we know that we're going to end up using this formula of a substance when 3 moles absorbs 50 kilojoules of energy. Well, once we identify our variables here, we just simply use the formula, the molar heat of vaporization, which is the heat over the moles of the substance. And then we're solving for the L. In this case, it's going to be 50 kilojoules divided by the 3 moles of the substance. When you plug that in your calculator, you end up getting a value of roughly 17 kilojoules per mole. And we normally would go to sig digs here, but the amount given should have been 3.0, so it is a little odd to just do one digit when the number is 17. But you know, for now, we'll just ignore the significant digits on this one. Well, I hope this clarifies heat transfers and latent heat of vaporization. The only thing that's left for you to do is to do the practice that your teacher ordains to you, okay? Because practice consolidates your learning.